In this video, I'm going to show you a nice trick to evaluate functions which look like e to the negative 2t times cosine 3t dt. Now, you have seen these functions in your calculus class, and you know perhaps know how to integrate them using integration by parts. Or probably you know you have a table of integrals and you can look this up. But I want to show you how complex numbers can be used to evaluate these integrals in a pretty easy way. You will see that it's far less painful than doing integration by parts. In fact, you will not need integration by parts. Okay, so the key idea is this. The key idea is to think of the integral and if you think about this integral, we can write this term e to the j3t as cosine 3t plus j times sine 3t. So we can write this as plus j times sine 3t dt, and that's from Euler's formula. But notice that this can be split into two integrals. So we can write this, maybe I just need to do that. Plus j times let's call the integral that we want to evaluate as I. And now you notice that this is the integral that we want to evaluate, right? This is I. Okay. Now, what's the point and why is it going to be easy to evaluate this integral using complex numbers? Well, notice that this integral is just the real part of this integral. If I'm able to perform this integration, I can take the result of that and I take the real part of that, and that should be my answer to this integral, right? Because I've split this integral into a real part plus j times the imaginary part. And you will see that evaluating this integral is much easier than evaluating this integral, because if you look at this integral, this is e to the, you can think of it as t times negative, actually we'll write it as e to the negative t times negative t times 2 minus 3j times dt, and that is e to the negative t times 2 minus 3j divided by negative 2 minus 3j. The integral limits are 0 to infinity, and when I plug in the upper limit, you will see that you get e to the negative infinity times some positive real number here, so that's going to go down to 0. And this is exactly what happened in the last video that I made. And you can go back to that video to see why that is 0 if you need a little more detail. And when I plug in the lower limit, I'm simply going to get 1 here. And so the answer then becomes 1 over 2 minus 3 times j. Let me make sure I get this right. So e to the negative t times 2 minus 3j, e to the negative t times 2 minus 3j divided by negative 2 minus 3j, and I plug in 0 to infinity. Yeah, it seems right. So my final answer is the real part of this, right? So the final answer I is the real part of 1 over 2 minus 3j, and we can compute that in one of many ways. You can either take this complex number and multiply and divide by the conjugate of that complex number, and that will give you the real part and the imaginary part separately. or you can take this complex number, add the conjugate of this, and divide by 2. I'm going to just multiply the numerator and the denominator by the complex conjugate of 2 minus 3j. So that will give me 2 plus 3j divided by 13. And so the real part, or rather, the final answer is the real part of this, just 2 over 13. I think that was pretty painless, right? No integration by parts.